You're okay? Okay. Well, first of all, let me thank the organizers for this very nice invitation. It's, of course, an unfamiliar setting, but I think this is a great initiative. And I also would like to thank all of you who are seeing or listening to this talk. Okay. So the talk is on asymptotic simplification for solutions of the energy critical wave equation. So in this lecture, I'll be discussing this equation, the energy critical wave equation, in the focusing case. And the interest of the focusing case here stems from the presence of nonlinear objects. I will clarify what I mean by that later on. And even though we're concentrating on this specific equation, the long-term goal and the hope is that the results we describe will be a model for what to strive for in other nonlinear dispersive equations with nonlinear objects. So the nonlinear wave equation is the equation in the brackets. It's the D'Alembert minus the semi-linear nonlinearity absolute value of u to the 4 over n minus 2u equal to 0. Initial data u0, initial data of the derivative u1. And this holds in Rn cross a time interval which contains the origin. The fact that we have a minus sign in the nonlinearity indicates that it's the focusing case because the linear part is positive and the nonlinearity is negative. So there's a competition between linear and nonlinear effects. Usually here you write the power p minus 1. And the fact that we chose p to be 4 over n minus 2 plus 1, which is n plus 2 over n minus 2, signifies that we are in the energy critical case, and I will explain what that means in a moment. For the initial data, we will be working in what I will be calling the energy space, which is the space of functions whose gradient is in L2, and the time derivative will be in L2. In the focusing case, unlike the defocusing case, which was studied extensively previously at the end of the 90s and beginning of the 2000s, there can be finite time blow up or solutions that exist for all time but don't scatter. By scattering, I mean that asymptotically in time behave as if they were a solution to the linear equation. I will give a formal definition later. So let me just review what we call the local Cauchy problem here. For this nonlinear wave equation, if you start out with small data, you obtain a global in time solution for positive and negative times. These equations are time reversible, so time will flow backwards and forwards. And for small data, the solutions will scatter. That is to say, they will asymptotically behave like linear solutions. Now, for large data, we can only have solutions in a finite time interval. And we can then have a maximal time interval. And this time interval depends on the function itself, not just on its norm, because we're in the energy critical case. So why is the energy norm critical? And here, by criticality, we mean a notion connected to scaling. If lambda is a scalar, u of lambda xt equal to u of lambda to the n minus 2 over 2, u of x over lambda t over lambda is also a solution. And this energy norm is critical because the rescaled solution and the original solution have the same norm. The norm doesn't change when you change lambda. That's the feature of criticality here. This equation has a conserved energy. The energy is written here. It's 1/2 grad u0 squared plus u1 squared, which is the linear part of the energy, minus n minus 2 over 2n, u0 to the power, the integral of u0 to the power 2n over n minus 2. It is easy to construct solutions that blow up in finite time, let's say at time equals 1, by considering the associated ODE. So we forget about the space dependence and we just look at this as an equation in time. And then for when n equals 3, the solution u of xt equal to 3/4 to the 1/4 times 1 minus t to the minus a half that's a solution. And obviously at t equal to 1, it blows up. Now, this of course doesn't come from data in the energy space, but we can use finite speed of propagation and cut it off initially. And then it's possible with this to construct solutions whose final time of existence is 1 and for which the norm goes to infinity as you approach 1. We will call this type of blow-up solutions type 1 or ODE blow-up solutions. This equation also has type 2 blow-up solutions. That is to say, solutions for which the final time of existence is finite, but the norm remains bounded up to the final time of existence. These solutions break down not because the norm itself explodes, but by concentration. What happens is that the gradient square is concentrating at the blow-up point as a delta mass. And the existence of this kind of blow-up solutions is typical of focusing energy critical equations. Examples of such equations go back to work of Krieger, Slag, and Tataru for the 3-dimensional case, Hilaire and Raphael for the 4-dimensional case, and Gendrich for the 5-dimensional case. And in this talk, we will exclude ODE type blow up. So we will study solutions that are bounded in the energy space up to the final time, and the final time may be finite or infinite. Let me give you some examples of bounded solutions that exist for infinite times. The first example is the scattering solutions. That is solutions which have final time, infinite final time, and such that there is a pair U0 plus U1 plus, such that when you subtract from your solution the solution to the associated linear equation, and you measure that in the H1 cross L2 norm, as t goes to infinity, this goes to 0. And that means that the nonlinear solution approaches at infinity a linear solution, so it has linear behavior. There's other so all small data are scattering solutions, and so they live for all time and remain bounded. Now there are examples which of solutions that remain bounded that do not scatter. And the first examples are non-trivial stationary solutions. Of course, if we forget about the time dependence and we just look at the x equation, we obtain a familiar nonlinear elliptic equation, which is well known to people for its role in the study of the Yamabe problem. And so non-trivial stationary solutions solve Laplacian q plus q to the 4n minus 2 plus 1 equal to 0 with an absolute value in there, and they're in h dot 1. And let me give you an example of such a solution. W of x, which is 1 plus x squared over n times n minus 2 to the minus n minus 2 over 2. This solution is well known in the Yamabe problem, but it was discovered a long time ago at the beginning of the 20th century in connection with the Sokolov embedding inequality. Now, it was discovered by Bliss. Stationary solutions don't scatter. And you can see that because if you have a solution that scatters, when you confine the norm to be just in space to be in a fixed box, then that will have to tend to 0 as time goes to infinity. And because the linear solutions have that property. And clearly a stationary solution doesn't have that property because it doesn't move in time. So this solution W is a very important solution in the theory. Now it has several characterizations. First of all, up to sign and scaling, where the scaling here is the same as the scaling of the nonlinear wave equation. They are the only radial solutions. So only W minus W are radial solutions together with their scalings. Up to translation and scaling, they're the only non-negative solutions. And this is a classical result of Gidas-Nirenberg, Gidas-Caffarelli, Gidas-Sprocket. So plus and minus W minimizes the energy among non-zero stationary solutions. So if we calculate the energy and we restrict ourselves to solutions in the energy space which are not zero, then W and minus W, their translates and scalings minimize that quantity, and that's why we call it the ground state. I should also mention that there are in abundance variable sign stationary solutions. So there's a whole zoology of solutions of the nonlinear elliptic equation with variable sign. There's other non-scattering solutions to the nonlinear wave solutions that I should mention here, and they're the traveling wave solutions. So they're solutions whose profiles rest the same for all time, but they're moving as time moves on. So examples of traveling wave solutions are obtained by using the Lorentz transformation. The Lorentz transformation leaves invariant the class of solutions to the nonlinear wave equation. And so we look at the stationary solution as a solution of the nonlinear wave equation, and we do a Lorentz transformation to it. And so this is what we obtain. For each direction L in Rn, which is subluminal, here the speed of light is 1. So for any speed that is slower than the speed of light, and any direction, we can find a traveling wave in that direction. And I write it like this. And then the horrible explicit formula of what happens when you do the Lorentz transformation is written here. And so these are examples of bounded solutions which do not scatter and are depend on time. So let me make a remark. First of all, in the radial case, there can't be traveling wave solutions because that would destroy radiality. So the L is 0, and the only options are plus or minus the scalings of W. And in a work with Ducaer and Merrill from 2014, we have proven that all the traveling wave solutions to the nonlinear wave equations are Lorentz transforms of solutions to the nonlinear elliptic equation. So these are all the traveling wave solutions. So what we're going to be interested is in the study of the long time behavior of large solutions to the nonlinear wave equation. And this study started with work that I did with Frank Merrill already more than 12 years ago. And the result that we proved is we called it the ground state conjecture. Other people call it the threshold conjecture. It states the following. Suppose that we start with energy smaller than the energy of the ground state, W. If the L2 norm of the gradient is smaller than the L2 norm of the gradient of W, then your solution will exist for all time, positive and negative, and will scatter in both time directions. If, on the other hand, you start with L2 norm bigger than the norm of W, then you cease to exist in finite time in both time directions. And finally, of course, there's the option that the gradient be equal, but the constraint that the energy be smaller than the energy of W makes this impossible by variational considerations. Finally, soon after, the threshold case, when the energy equals the energy of W, was completely described in a work by Ducaire and Merrill around the same time. So the question now, and this is what we're going to spend the rest of the lecture on, is what happens when the energy is bigger than the energy of W? When Merrill and I introduced around 2005 the concentration compactness rigidity theorem method to study this kind of issues, and which was used, for instance, in the proof of this theorem I just mentioned, our ultimate goal was to describe the asymptotic behavior of bounded in energy solutions as t tends to the final time in the spirit of the Soliton resolution conjecture. So now let me give you some brief background on the Soliton resolution conjecture. So since the 1970s, there has been a widely held belief that coherent structures and free radiation describe the long-time behavior, the long-time asymptotic behavior of solutions to nonlinear dispersive equations. So this is a belief, and this belief came to be known as the Soliton resolution conjecture. Now, the Soliton resolution conjecture is not, as I'm saying here, a conjecture, but a belief. It's a collection of conjectures. So roughly speaking, this says that asymptotically in time, the evolution decouples as a sum of modulated traveling waves and a free radiation term, which is a dispersive term solving the associated linear equation. Now, this is a remarkable statement in my mind because a priori, the dynamics of the long-time behavior of nonlinear dispersive equations could be extremely complicated. But this assertion says that if you wait long enough, things resolve into the nonlinear objects, and this is what we mean by the nonlinear objects here, sums of modulated traveling waves, and radiation, which are dispersive terms, which solve an associated linear equation. Now, the origin of this statement is very interesting in my view. It goes back to a puzzling paradox in a numerical simulation by Fermi-Pasta-Ulam, which was conducted at Los Alamos after the end of World War II and in the early 1950s, which was the actual birth of scientific computation. So in the work in the Manhattan Project, they needed large-scale computation, and they built a machine there at Los Alamos called the Maniac. And at the end of the war, Fermi thought that there should be uses for the Maniac in scientific work. And so he proposed to do a numerical simulation of a PDE that was too complicated to carry out by hand, but which the Maniac could carry out. And when he did this, he had a surprise, and he called this a minor discovery. And this was the first numerical simulation of a PDE. So I would span the scientific computation from it. But Fermi called it a minor discovery, this surprise. And this surprise is what's called the puzzling paradox, or the Fermi-Pasta-Ulam paradox. In the mid-1960s, so this is more than 10 years later, nobody understood why this paradox had taken place until Martin Kruskal brought the correct de Vries equation into the picture, and the fact that it has traveling wave solutions, which is something, of course, that goes back to the 19th century when Russell discovered the solitons for the correct de Vries equation in a channel in Scotland. Anyway, so Kruskal was able to tie the Fermi-Pascal experiment to the correct de Vries equation, and the traveling wave solutions to the KdV equations explained the Fermi-Pascal paradox. So Kruskal with Zabusky shortly after decided to do another numerical simulation. By then the machines were much better, and they did a very influential numerical simulation on KdV. And they discovered two very remarkable things. The first one was that for simple data, which was concentrated on one mode, once you run the evolution in the machine, for large time, this equaled a sum of traveling waves, of solitons. So that's the first thing that they did. And the second part of their numerical work was to take data which was the sum of two solitons and evolve them numerically. In the evolution, these two traveling waves eventually collide, and then something happens and they re-emerge after the collision, but they re-emerge unchanged except for translation. And this is what we now call the elastic collision. So this nonlinear equation behaves as if it were linear after the collision. So the first part of the experiment was performed in connection with the explanation of the Fermi-Pascal paradox, and this gives direct rise to the Soliton resolution conjecture. The second part of the experiment was eventually understood as a consequence of integrability. So the discovery of integrable nonlinear equations. And this was an important new concept in nonlinear science, which emerged directly from the Kruskal-Zabusky experiment. So integrable equations are equations that can be reduced to countably many linear equations. So, and they are not ubiquitous, they're quite rare, but somehow they appear in many important situations in nonlinear science. The Soliton resolution was first proved for a few integrable equations. Now, even in that case, the proofs are challenging, and there are issues that are still unresolved, for instance, in the case of KdV itself. There have also been results in perturbative regimes, that is to say, near solitary waves. Then there's many, many results in this direction. This Soliton resolution phenomenon has also been observed both numerically and experimentally in many settings. So the mechanism one observes for this relaxation to a coherent structure is simply that excess energy gets radiated to spatial infinity. And this can be seen in diverse settings, such as the dynamics of gas bubbles in compressible fluid. And of course, that you can see experimentally, and in the formation of black holes in gravitational collapse, which you cannot see experimentally, but you can see numerically. And let me just give you a preview of the next talk. You will see another numerical experiment for two-dimensional fluids, where you will see Soliton resolution taking place. Now, proving this conjecture in any generality for non-integrable Hamiltonian models is one of the major goals in the study of nonlinear dispersive equations. So let me now turn to the results for the nonlinear wave equations, which I'm going to call the asymptotic simplification results inspired by the Soliton resolution conjecture. So the first theorem is already roughly 8 years old. It's in joint work with Thomas Duicaer and Frank Merrill. And it states the following. Suppose we have a radial solution of the nonlinear wave equation in 3D. And 3D is important here. And let's assume that it exists for all time. So then there's a number, capital J. There's a radial solution of the linear wave equation, the radiation term. And for each little j between 1 and capital J, there are signs ij, and there are scaling factors lambda j, which we can order. First of all of the scaling factors are much, much smaller than t, which is the aperture of the light cone. So by the two less than or equal signs, I mean that the ratio goes to infinity. And with these parameters, we can show then that the solution u of t equals the sum of the rescaled solitons, plus or minus, plus the radiation term via L of t, plus a term which tends to 0 as t goes to infinity in the H1 norm, H.1 norm. And since our solitons here don't have a time, don't have translation in them because we're in the radial case, they don't appear in the decomposition of the time derivative, only the radiation appears, and the time derivative equals the time derivative of the radiation term plus a little o of 1 in L2. And there's corresponding results for the finite time existence too, but I won't discuss those here. So let me start by describing the key ingredient in the proof of this result. So this is the following fact. Suppose we have a solution, a radial solution of the nonlinear wave equation in 3D. And let's say defined for all time. And it's not identically 0, and it's not identically either a soliton, the W sub lambda. Then you have numbers r and eta positive, such that either for all t bigger than or equal to 0, or for all t less than or equal to 0, when you go outside the light cone, the translated light cone absolute value of t plus r, there's still energy for all times. So we call this the fact that there's energy channels for t bigger than or equal to 0 or t less than or equal to 0. So as long as you're not the soliton, you have an energy channel either for positive time or negative time according to the ingoing or outgoing character of the wave. And of course, for the solitons, you don't have this. And this can be seen as a mathematical quantification of the radiation of excess energy to spatial infinity. So at spatial infinity, once you take away the solitons, there's always some energy, and there's this radiation. Now, the proof of this bound relies on something that we will call energy channel lower bounds. Now, for the rest of the talk, I will call this fact here energy channels, just for the purpose of this talk. But let me now go to the energy channel lower bounds. And this is an inequality for solutions of the linear wave equation. It's a very simple inequality, simple to state, simple to prove. D'Alembert himself could have proved this. So let me explain this setting. We have n, we have 3 dimensions. We have R naught bigger than 0, and we consider a 1-dimensional subspace of H1 cross L2 as all the multiples of 1 over R comma 0. And the significance of 1 over R is that it's the Newtonian potential in 3 dimensions. 1 over R to the n minus 2, n minus 2 is 1. So that's the significance of this object. And now somehow this is an exceptional object and we need to rule it out. And the correct way to rule it out is we do the orthogonal projection to its orthogonal complement in this space. Then we proved with Ducaire and Merle in 2009 that if we have a radial solution of the linear wave equation for n equals to 3, then either for t bigger than or equal to 0 or for t less than or equal to 0, we have this lower bound. And the constant is 1/2. So there's always energy outside. Okay. So there's the exception of the solution, which is, let's say, 1 over R for R larger than R naught, and 1 over R naught for whose data is 1 over R naught for R less than R naught. And for that solution, using that 1 over R is the fundamental solution for the Laplacian, you see that the term on the left will go to 0. And so fortunately, we project out of this space, so the right-hand side would also be 0. But what this inequality says is that that's the only exception. Now, a key point of why this is useful for the nonlinear problem is that the ground state W is asymptotically like the Newtonian potential. And that's the connection between the two things. Now, this lower bounds for the energy channels for the linear equation easily give the energy channel property for solutions to the linear wave equation. Provided, of course, you have to change the R naught. So that's simple. Now, to pass to the nonlinear equation, you have to do iterative arguments that are very reminiscent of 2 elliptic ideas. First, the standard iteration arguments to gain decay or gain regularity in elliptic theory and gain decay at infinity, plus the fact that you need to come in from infinity, as in the moving plane method. These are philosophical comparisons, not actual comparisons. The next thing I want to mention is that there's a version that holds in the non-radial case for all odd dimensions, all n odd. So for all t bigger than or equal to 0 or t less than or equal to 0, we have the corresponding result for R not equal to 0 in the non-radial case. So these questions raise, issues raise the following questions. What happens is there an asymptotic simplification for the nonlinear wave equation for n bigger than 3 in the radial case, or in the non-radial case for n bigger than or equal to 3? The first, so that I will mention 3 relevant facts to these questions. The first fact arose in work with Kott and Schlag in 2014, where we showed that this lower outer energy bounds fail in all even dimensions, even for the radial case. And they fail miserably, okay, for infinite dimensional spaces. Second fact, which we did with Laurie, Liu, and Schlag in 2015, is that for all odd dimensions bigger than 3, there is an analog of our first channel of energy, outer lower bound for channels of energy. by the way, these two facts are established by using Fourier analysis. So now what happens in the higher dimensions is that you have a larger, still finite dimensional, but larger exceptional set. This set, the subspace spanned by these guys and is odd is still exceptional. And provided we project away from this exceptional set, we have this inequality. And the third fact is that all of these inequalities fail in all dimensions in the non-radial case, and they have infinite dimensional counterexamples coming each from each degree spherical harmonic. Okay, the fact that this subspace is the subspace P sub R naught we just saw here, you see, has dimension bigger than 1, even in dimension 5. This is responsible for the failure of the method of proof for theorem 1 working in higher dimensionals, even in the radial case, in the odd dimensional case. The reason is that there's only the one-dimensional scaling parameter to work with, and you cannot kill more than one dimension with that. And until very recently, this was a major obstacle in our way. Now, the fact that none of these estimates hold for the non-radial case, and the fact that there's a huge set of solutions to the nonlinear elliptic equation, which there's no classification, there's no quantification for it. This is responsible for the fact that there's no analog of theorem 1 in the non-radial case in any dimension right now. In spite of this, some weaker results using monotonicity after time averaging have emerged. So we can use, we were prompted to use monotonicity after time averaging from work in parabolic equations, in geometric flow problems, for example. But then the results obtained hold not for all times, but for well-chosen sequences of times. So here is what we get, for instance. The theorem 2 says that for any dimension bigger than 3 in the radial case, you have the decomposition analogous to theorem 1, but only along a well-chosen sequence of times. So this was proven in the odd dimensional case by my then student Casey Rodriguez in 2014. In the fourth dimensional case, the first even dimensional case, is due to Kott, myself, Laurie, and Schlag. And for the rest of the even dimensional cases in joint work with Hao Jian. So then the third theorem, we have scaling parameters, we have centers which remain within the light cone, we have Lorentz parameters, and we obtain the Soliton resolution with the traveling waves, which are solutions in the nonlinear wave equation. Okay, so let me just point out that the method of proof using monotonicity after time averaging, like in the last two theorems, cannot give more than a decomposition for well-chosen sequences of times. The example of the harmonic map heat flow given by Topping in 1997 shows this, where you get the decomposition and it's not the same for all sequences of times. So let me now turn to recent progress in the radial case for n bigger than 3 in the odd dimensional case. So in a series of 3 papers, which we posted at the end of 2019, we have proven the full decomposition for the radial case. So maybe because we lost some time, I will take 2 or 3 extra minutes if this is okay.
Of course.
Okay, thank you. So the proof of theorem 4, this last theorem, is the fact, has as its starting point the fact that you can prove it for well-chosen sequences of times. This fact allows you to start the dynamics when you're close to a sum of scale static solutions plus a linear dispersive term, because you go along the well-chosen sequences of times. Then once you put yourself in that setting, what you need to do is study the collisions of two or more scale static solutions with scales that are far apart from each other. And now we have to show that those collisions are inelastic, in contrast with the integrable case that was in the experiment of Kruskal-Zabusky. So these collisions are always inelastic in these non-integrable settings. And this is what gives us the full Soliton resolution. So let me just conclude saying what I mean by this elastic and inelastic stuff in the present setting. Specifically, we say that the radial solution that exists for all times is pure multi-soliton, asymptotically as time goes either to plus infinity or to minus infinity, when you have more than one soliton scaling parameters, such that your solution asymptotically, as you go to either plus infinity or minus infinity, it equals this multi-soliton. If our U is a pure multi-soliton going to time plus infinity and to time minus infinity, we say that the collision is elastic. And our our channel of energy property in 3D precludes this from happening. In the series of papers, we prove a slightly weaker version of the channel of energy, which says that if you start with a radial solution which stays close to decoupled static solutions, sum of decoupled static solutions for sufficiently long time, then either for positive time or for negative time, you have a channel of energy with a slight loss by a fixed amount. And this slight loss is what takes care of the new dimensions in those finite dimensional spaces. And this is enough to exclude elastic collisions. So thank you very much.